This presentation is on solutions and solubility. In a solution, the particles are so small that the solute cannot be filtered out. It always stays mixed. The particles are always in motion, so think back to the kinetic molecular theory for gases, and you can kind of picture how particles in the solution are moving. The volumes may not be additive, meaning that if you have 10 milliliters of one substance and you're going to add it to 100 milliliters of another substance, your total volume in the end may not be 110 milliliters. It might only be 108 because the particles can fit in between each other. And the solution will then have different properties than the pure solvent will by itself. A solution has two parts. It has the solvent, which is the component that makes up a majority of the solution and is the one in the greater concentration, which is usually water. If it's a solution that has ethanol as the solvent, then we call it a tincture. And the other part is the solute, the component that's in the lesser amount. There might be multiple solutes inside. Typical tap water has many, many solutes in it. Solutions can be made that exist in any of the three states. You can have solid solutions like dental fillings or 14 karat gold or sterling silver where you have a mixture of solid particles. You could have liquid solutions like saline solutions, vodka, vinegar, sugar water, or you could have gas solutions like the atmosphere or anesthesias. One of the ways to predict solubilities is like dissolves like. So materials with similar polarity are soluble in each other and dissimilar ones are not. So for molecular substances, water would dissolve anything else that's polar because water is polar, but will not dissolve things very well that are nonpolar. When we say two things that are soluble in each other in all proportions, we call that miscible. And when they are not soluble in each other at all, we say it's immiscible. So when we talk about concentration, we're talking about the amount of solute present in the given quantity of solvent. We can look at percent mass, which is the mass of the solute, divided by the mass of the solute plus the solvent times 100. Or we could do mass of solute over mass of solution is the other way that we can view that. We could do mole fraction, which is symbolized by the X, which is moles of A, divided by the sum moles of all the components. Molarity is the moles of solute per liters, and molality is moles of solute per mass of solvent in kilograms. Notice that molarity is of the solution and molality is just of the solvent. Solutions have a certain energy associated with them. It starts with the lattice energies. So lattice energies are that energy in between the particles that are making up your solid. So the Q's in here are the charges between your particles. And the R is the radius or the distance between them. And E is the energy. And K is just constant. That gives us a value for the energy. And so when an ionic solid dissolves in water, the lattice energy has to be overcome. So the water surrounds the ions and pulls them off one at a time. That's the process of hydration. The water has to get in between the ions, or the ions have to get in between the water molecules, the way you need to view that. So there are three steps to dissolution. Step one is you have to separate the solute into the individual components, which means you have to expand the solute. Step two is you have to overcome the intermolecular forces in the solvent to make room for the solute and expand the solvent. And step three is allowing the solute and solvent to interact to form the solution. So you have the solvent-solvent interaction, the solute-solute interaction, and the solute-solvent interaction. And so when you look, you start with the solvent, and step one is that you have to spread out the solvent, which is going to require a change in enthalpy to do that. Step two is you have to take the solute and spread that out, which is going to require a change in enthalpy to do that. And step three is where you allow them to interact with each other to make the solution, and there's going to be a change in enthalpy associated with that. So the total delta H for solvation is going to be equal to the delta H's of those three processes added together. So there's an exothermic situation where the enthalpy required to separate the solute and solvent is endothermic, but the interaction between the solute and the solvent is very exothermic, so the overall energy of the solution is going to be lower than where you started. So you have a exothermic delta H for that. And then the endothermic situation is where the interaction between the solute and the solvent is not very exothermic, and so the energy required to separate the solute and the solvent dominates, and so then you're going to have a delta H of making the solution that's positive. So if you look at the delta H1 and the delta H2 and the delta H3, it will give you all the possible delta H's for the solutions, and then you can determine whether or not the solution will form. So if it takes a lot of energy to separate the solute and solvent from each other, and you get a large negative enthalpy change for the solution, the solute and the solvent interacting, then you're going to get a small delta H, which means that you're going to have a solution. If you have a small delta H3, then you are most likely not going to get a solution unless the energy needed to separate the solute and the solvent is also small. So factors affecting solubility is the structure of the compound. Whether it's polar or nonpolar will matter. So nonpolar will dissolve nonpolar, polar will dissolve polar. Polar will also dissolve ionic compounds very well because of the charges. And the polarity of a solvent can be measured by its dielectric constant. The higher the constant, the more polar it is. The solubility of gases is small to begin with because they tend not to have strong intermolecular forces. That's why they're a gas in the first place. So they're not going to be highly attracted to the liquid. However, the solubility is proportional based on the pressure of the gas over the solution. We call this Henry's law. And so Henry's law is C equals K times P. C is the concentration of the dissolved gas, P is the pressure of the gas over the solution, and K is the constant for each gas. Sometimes it's also written as P equals Kc, and therefore your K, instead of being moles per liter atmospheres, will be liter atmospheres over moles. And K depends only on temperature. And so what you have is you have the gas in equilibrium above and below the solution, and so if you raise the pressure, you're going to force more gas into the solution. So at low P, not a lot of gas outside, so you have a low concentration. If you have a high pressure of gas, it's going to force more gas molecules into the solution, and so you're going to have a higher concentration. Solids tend to dissolve faster at higher temperatures. They also tend to have a higher solubility at higher temperatures. Not all. A lot of sulfates do not. It has to do with the interaction of the ions and particles with the solvent, and sulfate doesn't interact very well with water at higher temperatures. The only way to find this out is to do measurement in an experiment. And gases tend to be less soluble at higher temperatures, and the reason for that is because gases already have a little attraction for water, but now you're going to heat them up and increase their speed, and so now they're going to feel the attraction from the individual water molecules less and have a higher probability of escape. When we talk about a saturated solution, it means it has the maximum amount of solute that will dissolve in a given amount of solvent at that temperature. When we say it's unsaturated, it means that we can dissolve some more. And supersaturated solution means that we've dissolved more than should be possible to saturate it at that temperature. The way you want to think about this is in terms of the process of dissociation, which requires lots of solvent molecules to surround the solute particles, and therefore at some point you can run out of solvent and not be able to surround any more solute and pull them away. And so that's what happens at saturated. When it's unsaturated, you still have more solvent floating around. And when it's supersaturated, it means that there's some sort of stability that was formed in a saturated solution that you cooled down. And because of that stability that's formed, the ions stay in solution. But if you jostle it or shake it up, then those ions or particles will come out of solution very rapidly. An example of a supersaturated solution is sodium acetate crystals rapidly form when you drop a seed crystal in a supersaturated solution of sodium acetate. And this is an exothermic process, so a lot of hand warmers use this type of reaction. And so here's the sodium acetate seed crystal being dropped in, and within seconds the recrystallization occurs and a precipitation occurs, and eventually all of the solution will have solid in it. So this is a solubility curve where you are looking at the y-axis, which is the grams of solute in 100 grams of water, and the x-axis is your changing temperature. You can see here that you have the sulfates that are decreasing in solubility, but you also see that most of the other substances, especially the nitrates, increase in solubility greatly as you increase the temperature. Some don't change at all. Sodium chloride, potassium chloride have very little change in solubility with increasing temperature. Fractional crystallization is a way of separating a mixture of substances by their different solubilities. So because you can look at the different solubilities, if you were to have a mixture of sodium chloride and potassium nitrate, you could cool this down to near freezing, and your potassium nitrate will precipitate heavily, and most of your sodium chloride will actually continue to stay in solution, and so you can start to purify your solution and get all of one of the ions out. All right, so if you dissolve it all in water at 60 degrees and cool it to 0, most of the sodium chloride will stay in solution, most of the potassium nitrate will come out, and it will be a fairly pure sample because you're only going to have a few grams of sodium chloride mixed in there. Gases, again, this is the same solubility curve looking at the dissolving of gases, and you can see as the temperature goes up, there's less gas in solution. Some properties of aqueous solutions then. There are two general classes of our solutes. They are electrolytic and non-electrolytic. And so electrolytic are ionic compounds in polar solvents. Since they dissociate completely or dissociate a lot in solution to make ions, they were good conductors of electricity. They could be strong or weak, just like acids we talked about. They're electrolytic. We talked about KSPs already. So they could be 100% dissociated, which are strong electrolytes because they'll conduct electricity really, really well. Or they might only dissolve 1% or less than 10%. We call them weak electrolytes because they will not conduct electricity well. A non-electrolytic solution would be one that does not conduct electricity at all. It means the solute is dispersed, but it does not dissociate. So molecular solutions are like this. So if you're dissolving ethanol in water, the ethanol and the water do not come apart when that solution is formed, and so there are no ions floating around, and therefore you cannot conduct electricity, so it's considered non-electrolytic. Colligative properties are the properties that will change when you add a solute to make a solution. It's based on how much you add, but not what solute it actually is that you added. It is only based on the number of particles in the solution. So all molecular substances will have the same effect because the particles are the molecules themselves. So whether you're adding ethanol or acetone or any other molecular substance, all that matters is how many moles of particles you put in there. But with ions, it matters more which type of substance it is because it's going to change the properties based on how many ions it will dissociate into when it's in solution. The colligative properties that are changed really are the vapor pressure, and once you change the vapor pressure, it causes the freezing point to become lower, and it causes the boiling point to become higher, and that changes also the osmotic pressure. So when you have something dissolved, then it makes it harder for ions to escape from the solution because now they're attracted to something else in the solution. So you're going to have less particles with the energy necessary to be able to escape from the solution. So you have to raise the kinetic energy then to get more particles to come out. So the effect of this is that you're going to lower the vapor pressure above the solution. The introduction of a non-volatile solute will reduce the vapor pressure of the solvent in the resulting solution. The vapor pressure of the non-volatile component is essentially 0, and that's how we treat it. It does not contribute to the vapor pressure of the solution. However, the solution's vapor pressure is dependent on the solute's mole fraction. We already looked at some of these questions earlier with Rayoult's law, where the partial pressure exerted by solvent vapor above a solution equals the mole fraction of the solvent times the vapor pressure of the pure solvent. So we already looked at this in the gases chapter, right? We looked at it in reference to Dalton's law. It's the same idea. This is how it looks on a phase diagram. So you can see that your vapor pressure, which used to be here, has now shifted and is lower. So you get this different shaped curve, which means it intersects with the phase change points at a different point. And so here is where it intersects with the solid and liquid point. And so because it intersects down here, you've lowered your freezing point, but up here you have raised your boiling point. All right, the reason for the lowering of the freezing point also is related to the fact that when you have these other particles in solution, they prevent the solvent particles from being able to interact with each other and form the network that they are comfortable forming. So picture water making that ice network of water molecules, that six-sided ring that water molecules will make when they become ice. If you have ions in there, it makes it harder for the water to align themselves into that grid, and therefore it's going to make it harder to freeze, and you're going to have to cool it further in order for them to be attracted enough to become a solid. So this concludes our discussion of solutions and solubility that we'll do in this VODcast. We will follow this up in class, so we'll talk about some of the math of coagative properties, we'll talk about some of the other things about solutions, we'll talk about colloids, and we'll talk about osmotic pressure.